Hey, just started streaming somehow. Let me share the screen and try to solve the problem. Yeah. Given two integers n and k, the task is to construct a sequence here consisting of k non-negative integers such that their sum is less than or equals to n, and the total number of set bits in summation from 1 to n pop count of AI is large as possible. What is pop count of AI? You only need to compute output the maximum possible value of this one. You have n and k, okay, and then you want pop count of x denotes the number of 1 bits in the binary representation of x. For example, pop count of this. Okay, so this is nothing but total number of ones that you can write, right? And you want to minimize sum less than or equals to n, so you can always move the ones to this corner, right? So the AI value can always be 1 or 1 1 or 1 1 1 and so on, because you can always move them here, reducing the the summation and fixing this to be constant. Okay, that's one thing. And then whatever this sum is, you can further reduce those ones itself, and then you can reduce the sum to always be some maximum number of ones. Oh, okay. Sorry, the total number of set bits should be as large as possible. So one thing you can surely say is there will always be like 1 or 1 1 1 or something like that. Now, can you just be greedy? Have k non-negative integers. So you have k these positions, right? So it's simple. So you want maximum number of ones. So and you have to keep the summation low. So what do? First you will fill all the ones, and then you will fill all these things, and then you will fill all these things, and so on. As long as you can fill, as long as the value is less than or equal to that, you do that. So it's quite simple. You have an integer k. So you just have to imagine this column, okay, and you have to place ones in there. Placing them in the lowest position is best, right? Southern California, much like Arizona. So I'll have int answer equals to 0. For int I equals to 0, I less than, let's say 30 or something like that. It need not even be 30 because, okay, you have n left and you have k positions that are there, okay? So you can get int, let z equals to 1 power I or something like that. Now you can at max get how many jets from this n? Min of k comma n by z. These many things you can get, okay? So what do? You have n minus equals to q times z, and answer plus equals to q. See out answer. This is quite simple. Southern California, much like Arizona. I thought number of set bits, I actually complicated the problem. I thought number of set bits in this answer is should be maximized, I thought. But it's not that complex. I necessarily thought it to be more complex. Okay, A is done. Now we are at B. Hacks are disabled in this problem. It seems Milk Cat 2009 has a matrix A with n rows and m columns consisting of zeros and ones. The rows are numbered from 1 to n. The columns are numbered from 1 to m. The element in the ith row and jth AI scans every single submatrix of A consisting of R rows and C columns. So we will scan all of them. The AI considers the matrix clean if the bitwise XOR sum of elements in each of the submatrix equals to 0. Your task is to given various sets of integers n, m, r, say count the number of clean matrices of n rows and m columns with respect to scanning dimensions of. Oh, this seems complex, but maybe it's not that complex. Maybe it is easy. We never know. We never know. Right. Maybe it is all about the first R to C being 0 and all the columns and all the rows from there following some property. Maybe it's about that. Right. So let's say we want all of them to be 0. One thing you can say is in this row length of R and then in this column length of R, that should be same. Like if this was odd, this also should be odd. Okay? And then let's say you move and compare these two things. You know that this and this should be same and this should be same. Which means, see, if R equals to N and M equals to C, then it is quite big. It is just that total number of things should be even. Let's say the first one has been filled. Now let's think of all the things this top thing will be involved in. Or let's just think of this column. You can fill whatever you want all of here and then you can just flip this one as you like according to the sort of things. Okay, now that column has been filled. In that same manner, let's say we will fill all the columns. Okay, once you fill this one, you fill this and then this will get an option. And then you will fill this and then this will get an option. You fill this into poor thing and then this will get fixed. You fill this into poor things and then you get this thing will get fixed. So now you have R and all the columns have been done. Okay, from here, let's try to set one row down. Let's try to set all these things until C minus 1 and then this will get fixed and then all the things also will get fixed after that. And then let's do that again and again and again. Maybe that's the answer. I don't know. It's not that easy, but I think that's the answer. Is it deep too? Okay, now what's the formula I got? I can do it on pen and paper, but for you guys, I'm just doing it here. The answer I got is if you take a grade, okay, I'm doing it with touchpad. Uh, I will have everything except this one fill as I like, which would be r into c minus 1 cells. Okay, plus, and then I will fill all these things also as I like, 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 and then this will get fixed, this will get fixed, this will get fixed, and so on. After that, what will I do? I will fix all these things as I like, and then everything else will get fixed. So we can fix these things as we like is the solution now. Plus, what is this one? So if you see this one, what is this one? R minus 1 into an m minus c plus c minus 1 into n minus r. So maybe this is just the answer. Because if you fix these things, you have choice for these things, and once you fix these things, everything will become fixed. So I'll just go ahead with that. It's likely correct. So we have a big exponent here, right? But this is bounded with n into m, and n into m is bounded with 118. So this will work out. But we have to do ncr, we have to just do power, like we don't want ncr and everything, but we need power. Yeah, we need 2 power. 998244353. Free cells equals to r times c minus 1 plus r minus 1 times m minus c plus c minus 1 times n minus r. Int answer equals to power of 2 comma free cells. This would work. It's log of 118. It should be fine. We were just fun back then. Let me read C. Alice and Bob are playing a game with an array consisting of n non-negative integers. Alice goes first. In each turn, the current player must choose an array of n non-negative integers that satisfies the following conditions. All the values should be less than or equals to values in A, and that sum should be greater than 0 means it should not be entirely 0. They're all non-negative integers. The result should be equals to 0. After choosing an array B, the player updates the array A by performing AI AI minus BI. Damn. That's a crazy operation for the XOR. It's not XOR. I thought A will get XOR with B, but it's not that. Maybe it's not that crazy. Let's just try to read the problem. The player who cannot perform such an operation loses the game. So who can perform an operation? If there is no array such that XORs of BI equals to 0, then if they cannot form an array B, they lose. Right? So I think it's very much restricted because here they are telling determine the number of valid choices of for the first turn they are asking us. So that means it's like very much restricted. That's I think it ends after 2-3 turns itself. It gets most likely fixed after 2-3 turns itself. So what we can immediately we can try to see at some end cases, and we can also try to argue like what is the big power that these people have to make sure they win. XOR should be 0. See, let's look at it like this. See, whatever you subtract, there is a restriction here. Whatever you subtract, there is an obvious restriction here. Number of two powers you can subtract, a number of two powers you can subtract, number of two power one, zeros you can subtract, number of two power ones you can subtract. All of them are even whenever you subtract things. That's one thing you can say. But how does that matter? How does that matter? Subtracting everything even means you can just subtract even number of things. Like you can only subtract even number. Okay, that is guaranteed. And from the total sum, as long as there are two AI greater than zero, one can do one. Let me write some things down quickly. So losing position is A is not non-negative. A is like 1 to 10 to power 29, but yeah, we can think of it as non-negative. Losing position is only one non-negative, only one positive. Alright, this is a losing one, obviously, because everything must be zero, and then you have one thing, you must take something out of there, and XOR will not be zero. So this is the losing position. So how fastly can someone arrive there? Think of this case where B equals to A except for max, and XOR of remaining is less than or equals to max, is less than max. 1 minute. Or equal to max also will work, because you can just remove everything and then A will become all zero, and once A becomes all zero, even that's a losing position, right? So when will this happen and when will this not happen? We have to think of that. XOR of all the remaining things less than or equals to max or not. That means whatever max is, okay, this there cannot be a bigger bit. This bit people are having one. Again, this bit is being odd. And then this bit, and then some bit where max is zero is being one. Only in these cases, allies will lose. But we also have to count number of first choices allies can make such that she wins. Why are these problems becoming more difficult? I don't know. They should be direct most of the times, but now this is not direct. Maybe because of AI, they are just making out of problems. I got a new bottle, guys. There's some music things on that rhythm, I guess. But this is sucking one. At least this is not big sized, but this is like nipple sized, I guess. So I think it's not that gay to suck on this. It seems pretty weird though. I'll just drink it in normal fashion. Oops. Fuck. It's leaking. I shouldn't have done that. I shouldn't have done that. My laptop, my pant, and my floor. We were just kids back then. Everything sucked back then. What number of ways allies can lose, allies can win. So most of the time, if she has done something, maybe she will lose. Okay, let's just think of that. All these are odd. All these are odd. All these were like all the bits are even, and then the first bit that has been odd. So it's about the first bit that has been odd. Like if you consider all of them, it's about the first bit that has been odd. So I'm just trying to compare things. Okay, the first bit that has been odd in the total. Because there will be a bit that is odd that has been odd among the total. If someone is trying to remove everything else, there will be a bit. But if there is no such a bit, that means oh, wait a minute. Wait a minute. I think I left my consciousness in a sixth dimension. But I'm here right now. If this bit is the odd bit, there will be an odd bit, right? If this is the odd bit, allies will win. But we want number of configurations allies will win, number of first moves allies can make to win. So we clearly want to know what are all the winning and losing positions so that we can see what all losing positions can allies can give to Bob. Wait a minute. So there are only few losing positions. That means most of them are winning. I think I left my consciousness in a sixth dimension. But I'm here right now, right now. I have one question. If you have this shit, after you subtract even number of things from each of these bits, even number of 2 power this, even number of 2 power this, and so on, will the parity of these individual bits change or not is my question. Maybe it doesn't change. Okay, whatever has been formed, let's say you have been adding many big 2 powers now. Like here in this 2 power you'll add many ones, in this 2 power you'll add many ones. Then also the parity of bits will not change, right? And then let's imagine the subtraction. So this is constant. After all moves, the parity of bits is constant. Okay? But I'm here right now. So what we want is if max is having 1 and total is also 1. Wait a minute. I think I left my consciousness in a sixth dimension. Maybe in that case, you can just leave this one being non-negative and then remove this and everything else too. Why did I come to max? Because I thought I will just keep that. But then in that case, maybe you can just remove this Maybe in that case you can just remove max completely, everything else completely except this one. Maybe you can remove everything completely. So let's say this is that first bit where this is 1. Okay, whatever you subtract, one of such bit will remain, because you can only subtract even number of things, right? You cannot. So one of them will definitely remain among them, whatever you do. That means you should only make one of them remain and remove everything else in that bit. So what can you do for that? Keep this one, okay? All of this are 0 already. So you can remove all of them. And then here you're keeping this one, and then you will remove all of them. And then from here, from here, you can just remove everything. Everything else you can remove, and whatever the XOR comes, you will make that as 0. You'll take that XOR and then you will subtract that 1 from here, so that it's always possible. Always Alice wins. Always Alice wins means if Alice gives Bob something of total XOR not equals to 0 and two things greater than 0, Bob wins. This is sure. Alice should not give Bob a configuration where there cannot be two things and XOR cannot be 0. Okay, what if the XOR is 0 when Alice gives? That means XOR was 0 initially too. And XOR will forever remain 0. Now what are the moves? Like if the XOR is 0, I have seen that whenever XOR not equals to 0, someone can go to that first bit and remove everything else, and they can definitely, that's definitely a winning position for them. Because they can just remove everything, and then they can just remove XOR of all of these things, and then all of that from here, and then it just works out. But if XOR of everything is 0, then what? Oh, then Alice can just remove everything. And if she doesn't, then Bob fucking can. So in this case, Alice must remove all, because if XOR of all is 0, whatever Alice does, Bob also will get the XOR of all to be 0, because we have seen that. In this case, Alice must remove all. And in this case, as you can see, these bits where these things are odd and wherever these things are active, all of them can remain. Okay? One of them must remain. Any of them can remain. So it is just that many, I guess, then, because everything else must be deleted and then this will get fixed. Everything else must be deleted. You cannot keep two things. Wait a minute. I think I left my consciousness in a sixth dimension. One of them will remain, and then you cannot keep even one more thing. Then, because why? If you keep that, if you keep one other thing non-zero, Bob will win. So it's just number of active these bits. That's the answer in the other case. So it's a quite good problem. Like, I mean, I like the problem for the solving it has. Like, it's a nice problem. It's not too difficult. Maybe I came in a difficult direction. 998244353 is never necessary here. Like, it's always either one or it's either one or, oh, there are 0. Okay, if there is only one non-negative, then it's zero. Yeah. If there is only one non-negative, then it is zero. But which means n equals to one, and if n equals to one, it's zero. Now, if n is greater than or equals to two, we have to find that fucking bit that has XOR. That first bit that matters, because that's what matters, because that will sustain, that will remain whatever the fuck you do. So that first largest bit that matters. Wait a minute, I think I left my consciousness in a sixth dimension, but I'm here right now, right now. So let's just see if this bit, if number of times this bit present is even or odd. Okay, and also get the count maybe. Wait a minute, I think I left my consciousness in it. Maybe I should just name this as J. So if this shit is active, what's happening here? It's annoying. So if this has never happened, that means XOR is zero and then the answer is one. Wait a minute, I think I left my consciousness in a sixth dimension, but I'm here right now, right now. So sometimes the value can be up to 1 in 9 possible ways. Or there are no interactive problems, like I'm craving them, but there are n people attending a round table party numbered 1, 2, 3 up to so on and in clockwise order. Wait a minute, I think I left my consciousness in a sixth dimension. So there are n people in clockwise order. I prepared some gifts to distribute among them. Each person has a weight AI and a common field of view DI. On a common field of view D. Each of them has a weight AI and a field of view D. A field of view for person I consists of the D people sitting clockwise and the D people sitting counterclockwise from A. A total of 2D people excluding I. The happiness gained by persona is determined by the following rules. If the person I receives a gift and there are X people within their field of view who did not receive a gift, then they gain X times AI happiness. So if they get a gift and there are X people that hasn't get a gift, they feel better by seeing people that are lower than them. And if they don't get a gift and there are X people in their field who received a gift, then they occur minus X dot AI happiness. So people who got a gift will always be happy, but their happiness depends on the number of people who hasn't gotten a gift. And number of people who hasn't gotten a gift. I'm here right now, right now. So you can write this pair as, okay, you can write this happiness as, if you see that pair from this guy to that guy, okay, a field of view pair, you can write this X into AI as AI points on that direction, okay, AI points on that direction. It's like a 0 1 thing. You want to maximize the total happiness of the combined value, find this maximum value. D less than n by 2 is another thing that's there here. Yeah, that makes sense because it's pointless to have greater than or equals to n. But I'm here right now, right now. So if you try to see those as edges, okay, you have these edges going out, and then you have these edges that are coming into. If you have this edge going out, you have that edge coming into. If you can see that guy can see you. Okay? And if you look at one guy, he has this many people, that many people, and also those many people will come in, these many people will come in. These outgoing edges are all of the weights AI. Okay? The outgoing edges are of the weights AI. And for these things, if it is 0 0, it doesn't matter. If it is 1 1, it doesn't matter. But if it was 0 1 or 1 0, then it causes a problem. Okay? So if you see that weight, if you see one edge, if it is 0 and 1, you know the cost of these two being different. The cost of these two being different is AI minus BI based on whatever, which is 1 or which is 0. Okay? So ideally we want the bigger one to be 1 and the smaller one to be 0, so that we get the net positive. Okay? Can you make all of them like that? Like all the edges are having positive. Is that possible? Is that possible? Because that's an upper bound, right? All these circular edges are positive. Is an upper bound, right? You can't always do that. You can't always do that. So now the problem is about, you have this weighted graph. Okay? You have this weighted graph. You want to make one thing as 1 and the other thing as 0, 2. Then it will either be 1 to 0 or 0 to 1 based on that. Some edges will be positive or negative. My initial question was, can you make all of them positive? Maybe not possible. But if that is possible, that's an upper bound, and that's an answer. Wait a minute. Okay. Because let's say you have this bigger and then this bigger, bigger, smaller, and then much smaller. You cannot have this positive and then that positivity, because then this being positive means 1 0, and then also that cannot be positive. So you have these edges, some edges are like most weight, right? Can you just take those most weighted edges and make try to make all of them as positive? You take a most weighted edge and then you make that positive, so this will get 1, this will get 0. And then zero zero will not affect anything. See, sometimes 0 is the maximum you can get. Yeah, when all weights are equal, it is 0. Okay, if you keep few things as 1, what can you say then? Answer equals to, it also depends on number of 1 zeros are in the same pair again. It's not that simple. Okay, if you are already seeing the good pairings, okay, then answer equals to, among good pairings, number of 1 zeros. and based on that, their weights. It's not being that simple for me to see. I'll read E and then I'll come back. At least I'm not going after leaving C. At least I've done C. Now I can try to read this C, I think. Consider permutation P. Wait a minute. I think I left my consciousness in a sixth dimension. One value you can obviously get always is like you can always get max minus other things less than that. And if you have multiple maxes, then maybe you can keep all the maxes as 1 and then you can just keep all the remaining things as 0. And then maybe you can get max minus all of those things. You can have some positive and the neighborhood minimums as zeros. Wait a minute. I think I love my consciousness in a sixth dimension. But I'm here right now, right now. It's not that easy. It's not that easy. I'll come back, I think, I hope. But it may not be too difficult. It should be solvable. It should be written in a nicer fashion and then maybe it gets solved. Let me read E also and understand its complexity, and also read F and understand its complexity too without any fear. Only EF, only ABCEF are the problems, right? I'll get disappointed if I see the scoreboard, but let me just read it without any of that. See? Oh, F is being easier. D is somehow easy. With 300 also, it must be easy. Mm, yeah, it must be easy. Can I guess something? Wait a minute. I think I left my consciousness. Mm. Let's just see this value. Outgoing minus incoming. Okay. If that summation is greater than 0, can you keep that one and keep everything else 0? Yeah, you can do that. But can that happen for everything? Wait. You can see it in that way then. I think you can see the answer in that way. So this summation for all the ones is the answer is my assumption, let's say. Okay? For all the ones. Because one zeros are the one that involves cost. And then we are seeing it from the ones side. If there was one more one in here, then we would have considered this summation from that angle and from this angle, and they both will get cancelled. And when it is 1 and when that is 0, then that is fucking. So we can see the problem, we can see that summation in this nice fashion. It's a completely easy problem. So now we have an upper bound. Now the upper bound I have is positive values of this shit. So the problem is done. What I want is outgoing minus incoming, which is just prefix sums. I just want prefix sums. I just want circular prefix sums. Let me just take it like this so that prefix sums are easier to compute. Wait a minute, I think I left my consciousness in a sixth dimension. Or I can just do it like a sliding window, I guess. Let's say for the first thing you have computed that. When you move to the second thing, you will just remove that thing and you will add this thing. I think you can do it like a sliding window fashion. Wait a minute. So there was a nice way to see the problem. There was a nice way to see the answer. Just for once, get this summation and add them. That's a nice way. Like this is quite obvious, right? Outgoing minus incoming. I don't know why I haven't seen that. I was getting that, but I wantedly haven't seen that somehow. I was intuitively like just getting that. Like try to look at this and keep them positive. It's one of the basic solutions anyone can think of. C is much difficult than this, I would say. But my implementations are cool, right? So see how I'm going to implement this thing. Wait a minute. This will guarantee that they won't intersect the front and back. I hope it guarantees that. It looks like it guarantees that. I don't even need prefix sums, so I'll just do this. And then what will I do for int val of n? Let it just be val of n for now. I will consider sum of minus previous n things and next n things. Okay. So how does that start? For int I equals to 0, I less than d I plus plus, cur plus equals to a of I plus a of 1 plus I remainder n, which is not needed, but let's just put that. And another thing would be minus 1 minus I, but we can add n. We can add more also if you want to. We can add 2n for safety. N is enough, I guess, but n is enough. Let's not add 2n because at max it is less than n minus 1, right? So this value is less than n, so n works. Now I will do it like val of 0 equals to 2 times d times a of 0 minus cur, as we thought. For int I equals to 1, I less than n, I plus plus. So now what you have to do, you have to update the cur. Okay, you have a value here, you have 0 here. You want to subtract from 0 minus d is what you want to subtract. Okay, you want to subtract I minus 1 minus d. That's what you want to subtract. Cur minus equals to a of I minus 1 minus d plus n, remainder n. Cur plus equals to a of I plus d plus 1 plus 2 up to so on I plus d. Here I used I plus 1 I minus 1 because I'm kept 0 to my d index plus here we have to add I plus d remainder n. So now we have our curve. If val of 0 greater than 0, answer plus equals to val of 0. Val of I equals to same as above 2 times d times a of I minus curve. And if val of I greater than 0, answer plus equals to val of I. See how the answer equals to 0. It's quite obvious, it's quite simple. Anyone can just solve this problem quite easily, except me. Did I miss something? Have I fucked this contest up? One, two, three, and d equals to 1. So for 1, it is negative. For 2, it is 0. For 3, it is 1, 2, 3. So I haven't fucked this up. Something is wrong here. Probably this is being wrong. See, this can be 1. 3 into 2 minus 1 is not that much. Wait a minute. Wait a minute. I think I left my consciousness in a sixth dimension. Let me see curve values after all these things. Curve is being 5, 5, 5. So for 1 it is 5. For 2 it should be changing. For 2 it should be 4. For 3 it should be 3. Oh, okay, this will get added, right? Three, 15, 26, 85900. There is a hole there. I forgot about the hole. Without the hole, everything is same, right? So this problem is quite direct, quite simple, quite good too, I would say. It's not a bad problem, but it's very easy to guess. That's why I didn't like it that much. But it's a good problem. It's like doable by anyone. It's like doable by anyone. Like simple idea, simple problem, simple guess too, if you think so. If you want to see in that way. So SI is number of inversions in the prefix, where the square parentheses denote the inversion bracket notation. I never knew inversion is a guy name. I actually, damn, Turing Award for his pioneering effort in programming languages and mathematical notation, resulting in what? The computing. Inversion somehow feels like inversion. It's there cannot be a better name for inversion. Oh, that is different. This is different, maybe. Inversion is different. Yeah, inversion is another. Iverson. Fuck, my eyes are fucked, maybe. Wait a minute. I think I left my conscience. Iverson, okay? Fine. Iverson bracket notation. For each position I you are given a condition in the form of either pi equals to x or si equals to x. Your task is to reconstruct the original permutation p. It's guaranteed that a valid permutation always exists. If there are multiple valid permutations, you cannot put any of them. So you were given either the value of pi or you were given the value of x si, and it is guaranteed that a valid permutation always exists. So it's like a nice problem. It's like not too difficult problem, I guess. It can be difficult too, but yeah, it's likely a nice problem. What we have to do is we have to get a solution as quickly as possible here now. You're either given pi equals to x or si equals to x, and also the fact that at least one valid permutation exists. Using these three logically, you have to deduce find at least one valid permutation. So it's obvious that if all the permutation is given, you can do that. It's never contradicting. That is there for sure. Let's say there is a permutation. Let's look at that valid permutation because they gave that it's existing. Let's say there is that valid permutation. Okay. Now let's try to look at the problem once again. For all the p's, that valid permutation will perfectly match. And for all the s's where ss are equals to 0, that valid permutation will also match that. Okay. You were only given that for all the prefixes. If you know all s's, then also you know the answer, because you know number of inversions here, you know number of inversions here, which means you can know number of inversions here. So that means you can know number of things greater than this over here, which means you can get the relative ordering for everything. But when things are mixed, how the fuck can you get something? When things are mixed, maybe there can be multiple, but still you should get one that satisfies everything. So that's what they are showing. Piece SS and then PSP, PPPS, PSP. Will a cat come now? Closer to me. Wait a minute. I thought I left my consciousness in it. If you have SS, I think seeing adjacent things will give us a lot of information in here, maybe. Maybe it doesn't, maybe it does. Maybe you can find something for all the things. Let's look at the lost S. You have some piece here, you have this lost S. Wait a minute. Wait a minute. I think I left my. I'm thinking like if there is one S and some B's and then S, what then can you say? I think I left my consciousness in it. Yeah, let me read F2. Maybe F is a bit more direct because that had more solves. A brave group of M people decides to head up the mountain to hunt the beast. M people. The mountain locations, I'm getting susu. The mountain locations and trails can be modeled as a functional graph G with n vertices. Functional graph is a directed graph with n vertices and n edges where every vertex has an out degree exactly 1. So those are nice graphs, I know them. They just go and then end up in a cycle. They just go and end up in a cycle. Also, it is additionally known the mountain trails do not ever form self loops, means the circles are not non-redundant. They will always go into a cycle because otherwise they keep on going forever, right? Mhm. So I know what a functional graph is. The group will choose exactly m distinct vertices to form their initial starting set S. A starting set S is defined as successful if every vertex U in the graph is reachable from at least one of the vertices V belongs to S. There are NCM possible ways to choose the starting set M. I'll just go to this one now. Not just Susu, I mean how to go to. So what I will do is I'll read the problem and then I'll go and think and come back. However, there are NCM possible ways to choose the starting set of size M. They define the value of a graph G as the number of successful starting sets it has. If every vertex U in the graph is reachable from at least one V belongs to S. However, the exact layout of the mountain trails is unknown. This seems too stupid. Every leaf should be taken and then remaining things can go anywhere. So the problem is quite simple. But then what do they want? However, the exact layout of the mountain trails is unknown if the destination of the single outgoing edge from every vertex is chosen arbitrarily from the n minus 1 vertices excluding the vertex itself. There are n minus 1 whole power n possible functional graphs. Given n and m, your task is to calculate the sum of the values of all n minus 1 whole power n possible functional graphs. Since the answer can be large. Okay, this seems fun. This doesn't seem impossible, but it seems a bit fun. You have to just get the answer for that. First, you can very precisely write what's the answer for this shit. Oh, I'm gonna have to go and charge my laptop. See, you have some cycles, okay? And then you have some paths to these cycles, like trees. When they say all of them should be reachable, these leaves should be reachable too. So those leaves must be taken. Okay? All the leaves should be taken. All the leaves should be taken. And let's say there are L leaves. All the leaves should be taken. So you have NCM possible ways to choose the initial starting set. So now how many ways are there? You have n minus L cm minus l. If this is positive, this will always be positive. If this becomes negative, answer is 0. You want this summation over all possible fucking graphs. Okay? So if you know number of graphs with L leaves, 1 leaves, 2 leaves, 3 leaves, and so on, this value will become fixed with respect to that, right? So and then independently of M, you can find that answer. Can you find that? Can you find number of graphs with 1 leaf, number of graphs with 2 leaves, number of graphs with 3 leaves, and so on? How difficult is that? So if there is like L leaves, if you remove that, it will either form, it will have L minus 1 leaves or L leaves. Because if this is not having anything else coming into it, then it will have L leaves. But this is not that common. That is not that simple. That's not that simple. Maybe it is simple. So you can have n minus 1 and L leaves. So now it's becoming n minus 1 and L leaves. So yeah, this GP is like, maybe it's writable, but yeah, it's like if it is like two parameters changing, then it's not that easy. Maybe then it's not the right way to see it. Maybe there is some other easy way to see this thing. It's quite simple. Number of assignments such that number of leaves is this much. It's quite simple, but so let's look at that. Okay, let's look at that. So let's say these are the leaves set. That means none of them has chosen that. These L things, none of them has chosen that. Some L particular things, none of n minus 1 have chosen them. Okay, none of them has chosen. And then you want to find number of ways where you can map these n minus L things, and then you have to map how many these n things you have to map to this n minus L thing such that this n minus L is an onto function, so that all of them will get something. I think I left my consciousness in a sixth dimension. The problem is solved, huh? Stupid, simple, easy problems. See, number of onto functions, if there are n elements and m elements, we have several formulas for that. Okay? We have formulas like one thing being left out, two things being left out, three things being left out, and so on. But what all we want is for same value of n and different value of m is what we need. Right? That's what it is like. You want them to be onto, at least something should map to them. Ah, there is one more condition, something should not map to itself. Among these n minus l things, you have another condition that they should not map to themselves. Okay? And then you have these L things. Can you first map these n minus L things to these things so that you have few things that are left out? Or can you choose a subset that will be touched by this L? Means this L will make it 1 1 and onto. Sorry, not 1 1 and onto. And then these remaining things will make it. I think you can write some 2D formulas again. You can write some 2D formulas again, I think, but you can write some 2D formulas like number of identities that are there, and then once you remove them, you want the remaining to be onto. The only problem is some things being self loops. And then if you remove them, one thing, two things are there. Should we use just onto formula and then just try to remove things, or you have this fucking easy formula, which is quite obvious. You just make, 2% charge. You just make these k things are empty. You remove all the bad cases. And maybe you can write some bijections. Maybe you can write some DP, and then it can be solved. And then this shit can be solved in O of n itself. Maybe. Maybe I'm foolish. Maybe I'm blind. Thinking I can see through this and see what's behind. We want for all different values of L. If you can get number of onto functions on here without any self loops, we are done. Okay. Maybe I'll use pen and paper for a while. It's counting. I can even use generating functions for counting if I want to sometimes, but you have n minus L to n minus L. If you know without any self loops, number of things that will be left out. Even then you can write it. N to n minus L on to no self loops. You want this count, let's say. Okay. I think it's fair to assume that we compute it for all L. We compute it for all N. I think it's fair to assume that we compute it for all L. Other than that, computing it total might be not that easy to like, because the problem has been splitted like this, right? But if that's not being possible, then we have to combine both and then count together. But I think that's too complex for this problem to combine both. I think easiest is you can somehow compute this without doing much. Like let's say I will just try to find number of onto functions itself from n to n minus L. Okay, number of onto functions from n to n minus L is none of them are empty, but one of them is empty. Let's try to see like that. Okay, we want none of them are empty, right? Let's say there is one of them is empty. Okay, if you try to see that at least one of them is empty, let's say. mm, so that empty one has been left out completely. Let's say this particular thing is empty. If I try to write the first thing that has been empty, if I try to write like this has been empty, then it's again principle of inclusion and exclusion. Then it will become the same known mode for the same known formula. But does that same known formula has repetitions? See, it's always nck into n minus k whole power m. But if m is changing, why is it n minus k whole power m? After removing, okay, this is from m to n, I think. Why can't it be reverse? Let me write it in the reverse direction. I know the formula. Why am I even looking at this? I can just write it, I think. So you have total, which is n power m. Let this be m. Total is m power n minus one of them being empty, mc1 times m minus 1 whole power n plus nc2 times m minus 2 whole power n, and so on. So if you try to say these things, I think there can be a recursion where you can write a recursion from n to m to n to m minus 1, because you can likely see m minus 1 would be m minus 1 whole power n minus m minus 1 c1 m minus 2 whole power n plus m minus 1 c2 m minus 3 whole power n, and so on. You can say that you can write mc2 as m minus 1 m times, okay, this is on 2 of n come of on 2 of m, let's say on 2 of m minus 1, let's say. You can write that as on 2 of m equals to m power n. Okay, if you just subtract those two, it is m power n m minus 1 whole power n. And no, 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 not subtract, like, yeah, you can write that as minus m times m minus 1 c0 into m minus 1 whole power n minus m minus 1 c1 whole power m minus 2 whole power n, and so on, which will work out, I believe. So it is m power n minus m, so it is m power n minus on 2 of m equals to m times m minus 1 power m minus on 2 of m minus 1. So number of non-onto functions seems to be equal to number of non-onto functions here times m times that. So that means if you have onto of m minus 1, you can immediately get onto of m using the same fucking formula that I wrote now. Okay, now we have formulas for all the onto functions, like onto of m minus 1, onto of all the things. But we have this additional restriction that this cannot go to that. How do I see this formula that I just wrote now? At least one of them is left out. These things we are trying to see. Number of such permutations. Okay, when if at least one of them is left out, maybe when this is left out, how many things will be there? Total number minus, I'm not able to see this bijection, but when this is not left out, okay, when this is not left out, that means for all the remaining things, okay, when this is left out, somehow the formula is true. Let's just keep it like that. I'm not able to think of about how the formula is true. But now you have this problem where some of them are like that. Okay, you have that problem now. Let's say you have on two of m's, you have that for all length. Now to tackle this problem for this length, how can you do that? Let's say you have on two of m values for all of them. Okay, somehow you had that, you had those values, and then you have this thing where now it's on two, but some of them are like straight angles from this lm. How can you do this one now? Let's just find this one first, and then let's remove, finally let's try to remove the functions with L leaves. Now let's try to remove the L leaves. Let's say you have this one. Now let's try to remove the count this thing separately. Let's try to count this thing separately with at least one leaf. With at least one cycle. Ah, but that's not easy now because then the value of n will be reducing. If n is also reducing and m is also reducing, that's not easy. It cannot reduce n that much, but whoa, it's not just number of leaves. It's not just number of leaves. It's more complex than that. When you have all the leaves should be taken, and when you have pure cycles, at least one of them should be taken. So it's not that simple. It's more complex than what I have done. I have 30 minutes how to choose one of these problems. What has more solves? Both are almost having equal solves. So we want to count number of graph comma good ones. Where good ones are some of the marks that has been done. We want to count these pairs. Like I think it's actually good that this is not what I have to count. Now I actually have more to think in the problem. That's also a bit nice thing. Maybe I have to come up with a better one, better solution now, right? That's actually a nice thing. That's a bit of not a dead end that I'm not able to push further, but something to think further. For each vertex is chosen arbitrarily from the domain and also in itself. Given n and sum of values of all. I think number of successful starting seems bad now. Like it's easier, it's likely easier to count number of unsuccessful ones. I think so. Number of unsuccessful one is where one leaf is left out because you can just have these cycles, okay, and then you have some leaves. Counting that at least one of them is taken, at least one of them taken, is not that easy. I think. I have to go to washroom and then I'll think there. Okay, consider everything in mind. The problem is a bit different now, but all of these are leaves, right? And now the problem here is from this L and this N minus L leaves, it's not just on to. It's there are no. It's like there are no self. It's not just onto, it's like there are no self loops. It's like there are no self loops. All the leaves are taken, okay? And then there are no self loops. Like from I to I, there are nothing. And also, there cannot be no independent circles among themselves. Among this n minus L to n minus L, if there is an independent thing this should come and definitely touch one of them. Okay? That's another thing. Among all the things that are forming, we have to subtract things that are onto, things that are like independent. Okay? Let's say jet things are being independent and everything else is being touched. Okay? You can choose those jet, and those jet things are either going among cycles themselves, or they are doing like single loops, or they are doing cycles among themselves. Okay, let's say there are jet things that are doing that. So all those jet things can be removed from here. So it will be L n minus L minus Z, okay, 2 L minus, sorry, n minus L minus Z, because these jet things are cycling themselves. And then what is this? This is the perfection that we want. This is the perfect thing that we want, where there are no self loops, no independent things. Okay, whatever this is that we want. So what we want is W, let's say W of n comma L equals W of some set being cycles among themselves. This is W of n minus z, comma, L, things helping, times NCZ into Z factorial. Because these are permutations is my assumption. Total equals to n minus L whole power n equals to onto. All of this should be onto again because on this set, total onto equals to this is just e power x minus 1 whole power n, it seems. I can understand that exponential generating function thing, I think, because this being empty, this being empty, this being empty, we want none of them to be empty. Maybe that's why it is just e power x minus 1 whole power. If there are m things here and n things here, it would be e power x minus 1 whole power m. And coefficient of x power m will give us okay, number of onto functions equals to choose a set, and on that set apply permutation, and choose this other set, on that apply This is number of onto functions from n things to n minus l. Okay. That's being equals to choose a set and apply permutation on that. And what is permutation? E power x is permutation, I guess. 1 by 1 minus x is because yeah, if everything is if you keep n minus 1 factorial, so it is 1 by 1 minus x. So product of two things is choose one thing, apply permutation on that, and choose remaining things, and then so if you have L, which is a constant value, let's say L is a constant. L is a constant, and then you have n things that you're applying onto. Then e power x minus 1 whole power n is just number of onto functions. Right. That's just number of onto functions. And among those onto functions, you can split that as choose a set, apply permutation on that, and then on remaining things, okay, I understand this one. Not getting it. Okay, this is definitely not what I'm trying to count. There are many levels here. It's not that easy. I think I should have tried the other problem itself. Yeah, this is likely much harder than E. But can I get it? Maybe even after the contest, can I get this? Maybe this is more easier. But now coming to this or that, I fucked up the contest. I know D will have more souls. E will have more souls now. Maybe not that bad. I will solve it. Like maybe I'll improve my combinatorial skills if I do this. What all can I do? What is the simplest thing here? Like if there are some such simple cycles, at least one of them should be chosen. But we have M always. Like how the fuck can I write this? We have to start counting from somewhere, right? I was trying to think something, but then it made no sense after a while. Ah, wait. And I didn't wanna write a song, cause I didn't want. I still think I hold on. I didn't wanna write a song. Okay, these M things are mapping onto this thing. Let's say you have some graph here, you have some computation here, and these M things are mapping onto that, let's say. Okay? Yeah, these M things are selecting these things. You have N, you have M. Wait. You have N, you have M, and then you have this bijective mapping where also these M things will come onto that. And now the condition is that this N cannot just be an independent cycle among themselves. This M is a fixed value now. This N cannot be an independent cycle among themselves. And the whole thing should be onto. The whole thing should be onto. Okay? You have N, you have N. Now the whole thing should be onto M plus N. Is it e power? Okay, if a normal formula. Show you off. Tonight I wanna show you off. Million bucks. I'm getting something. I think it's definitely from a set of m plus n to n. Something's going from a set of m plus n to n. That seems to be the simplest representation of this complex thing that's happening here. And then if I look at all these mappings, what are all the good mappings? What are all the bad mappings? If there is a cycle here among these things which is not being mapped by anyone, if there is something which hasn't been mapped by anyone at all, show you tonight. I wanna show you a million bucks, a million couldn't. If you're only looking onto functions from this to this, we have that, let's say, somehow. Okay, all the onto functions from this to this can be treated as product of some of them being single to single. Single to single, and then someone approaching them is also bad. Okay, let's say you somehow have, now this generating function equals to, let's say you have onto without any. See, simplest way I can see this thing as, you have n elements, okay, mapping to n elements, and then you have some other m indexes, let's say. Okay, this m factorial, let's say we can just remove, and then there is a mapping. Now I'm trying to see these mapping maybe in terms of exponential generating functions or so. Like in this mapping, what we want is, we want we don't want these cycles to be present and be alone, or we don't want something that has not been touched by anything. So that's what we want. See, we don't want something that hasn't been touched by anything. If you see this mapping, like where everything else is mapped, this will form the graph, this will form the mapping that we are trying to assign, as assignment that we are trying to do. And then we don't want these single things, we don't want these cycle loops in here. That's the thing. But the complexities are arising because from single to single cycles we also don't want them. That is just stupid. Like if only like self loops were allowed, maybe I had some chance on this problem. But even with self loops, maybe it should be solvable. Maybe it is not that difficult as I'm thinking it to be. All I'm saying, let's give love a chance. This is the simplest way to see like n plus m going on to this thing. And let's just also say that this is an onto function. Okay. Now what's the problem? Now the problem is formation of these things and formation of one to one things. This is just the problem now. Okay. But formation of this one to one things, even if something on comes onto them, it's a problem. Okay. Here if something comes onto them, that's not a problem. Let's say you somehow have onto that cannot come onto themselves. Okay, let's say you somehow have that. Okay, you have that onto that cannot come into themselves. Maybe let's say you have that somehow for all n. Why did I rub my eye this bad? I have to go and wash my eye maybe a bit. I hope I don't look that bad. If there are any girls watching, you can always approach me. You can find my WhatsApp group. You can then text me on WhatsApp, and maybe we can go on some dates, and maybe we can have some fun, and maybe we can do some things. If only you want to. I'm not like using my platform to get chicks. Okay, it's a choice. It's not like mandatory to view my streams, I guess. No, where are we? You know why I talk shit on streams? I assume that it's 3 hour long streams. People can't find whatever the shitty things I say. That's why I talk shit on streams. Okay, now let's say you somehow had that. Among these, what are the things that can go wrong? Among these, the things that can go wrong is some things that are being left out. That's all. Some cycles being left out. That's all. You have onto everything else. is being touched, have onto, maybe only these cycles are being left out, only these are the things that are left out completely, some things that are being like this. So now how can you think of this problem? Now this problem is, now this problem is whatever the fuck you had here before, whatever the fuck. So I'm trying to see the problem as n, m is a constant, and then you have an n here, okay. I'm trying to see this mapping being onto, this mapping not having self loops. Okay, let's say that that mapping, we are trying to see that mapping for different values of n's. Okay, somehow we have that. Let's say that can be written as, choose some things over here. Okay, they will be forming cycles among themselves, pure cycles, leftover cycles. Okay, so this is just a permutation without degenerate. This is dearrangement, permutation without something's going to themselves. E power minus x, contest is done, it seems. So that we know it is e power minus x minus by 1 by x, it seems. Okay, so choose some subset, and then that subset being a degenerate, and then remaining things being a perfect onto, plus all of them being chosen, right? Because this is a perfect thing that cycles that have been removed completely, this set has been removed completely, things have been chosen and none of them, even m things are not coming onto them. And then what is the remaining thing? This is when you have remaining things and m things, these are onto, and if there is a cycle that will come onto that, one of them will come onto that. So it's like exponential generating functions getting multiplied, and if this thing goes there, it is e power x times 1 minus x times whatever this exponential generating function we have. So in that sense, I know this function that I want equals to, maybe if I just know this, brute force this somehow and get this onto no self loops, have m extra things. What's the answer? If I just know that, maybe I can just expand these things. I can substitute that as its exponential generating function here, and then I can just maybe expand these things and multiply the shit and maybe have my answer for n, coefficient of n. Okay, now what is this thing? You have n things, you want this to be onto, you don't want any self loops here. How do you compute that? Okay. You want them to be onto, you don't want self loops there, and that's all. And that's all. And once I have those coefficients, then I can write that, expand that exponential generating function, and then maybe I can expand these things too. And expanding this thing is not that difficult. It's just e power x minus x into e power x. Like it's just x power n is known. And then in O of n, we can get x power n's coefficient. So maybe it actually works, and if it works, it's weird or crazy, right? So if I have these coefficients, maybe it just works. And how to get those coefficients now? Let's just, okay, having all number of onto functions, let's say you have all possible onto functions. Let's say you somehow have the onto function formula, okay? And then now you want to remove some self loops, things where these things maps to themselves. How to see them? Where these things map to themselves. Let's say those are like these jet things are mapping to themselves. Remove those jet things, because these jet things are, we know what they are mapping to already. And if you see the remaining things, what are they doing? They should be onto among themselves, right? Maybe I'll write on. I can't visualize. I'll use my notebook. So we have n plus n. We want this mapping to be onto, and there are no single things. Okay. So let that be, because m is a constant. Let that be onto and single ontos. Let's call it ontos of n equals to, okay, onto of n equals to, m is also there, onto of n equals to, we have some singles, let's say, let's choose those singles, z specific singles, nc z, and then you have chosen those singles. Now other things mapping to them is not an issue to you, okay? Now you have m plus n minus z things mapping to n things again. And all I'm saying. See, the cycles give out, it's an exponential generating thing because the cycles give out that. Okay. No, no, no. I can't be writing something wrong that's here. I cannot say that you can remove these things because some other thing can come to here. And you cannot say that you can keep those things because they are already, their onto is being satisfied by this thing. Ah, there is another issue here. I cannot choose, two people cannot choose the same thing. That makes everything fucked up. I'm just ending the stream here, guys. I'm ending it. Two people can choose the same thing too because that's another issue we have. Fuck it. It's not easy. It's not easy. I'm ending it here.